Of Terrorists and Trees, an exploration of some aspects of graph theory of interest to computer scientists. In March, America goes mad. 64 universities compete against each other in a sport called basketball. I realize that since so many of you are not in America, I should perhaps use as an example the world's most popular sport, namely Quidditch. In March Madness, you see pictures like this. All that this picture conveys is who plays whom and when. We could draw the same picture this way and it would convey the same information. A graph is simply a picture of dots joined by lines. The lines don't even have to be straight. All that matters is which dots, which we call vertices or nodes, are connected to which by lines called edges. For example, here's a portion of the New York City subway. The lines actually have different colors, which has some meaning, but for us, that doesn't matter. All that matters is that you have lines that connect different stops. Although in some cases, you might have lines that cross each other, but that does not mean there's a stop there. Here's another example of a graph. I've labeled the nodes paper, rock, and scissors after the kids game, where two people will name one of these three items, and if one person names paper and the other names rock, the person who names paper wins. If one person names rock and the other names scissors, the person who named rock wins, and if one person names scissors and the other names paper, the person who named scissors wins. This example indicates that we might want to put down a direction for our edges, like one-way streets, to indicate who beats whom. This is a directed graph. Before we had an undirected graph. Here's another example of a graph, an undirected graph, where in this case the lines have a meaning. In this case, two nodes are joined by an edge if they're friends. The type of graph we saw for the sporting contest March Madness is ubiquitous. It's called a tree, in fact, a binary tree. In this section, we're going to study aspects of trees and more general types of graphs, especially planar graphs. And the graph theory is of independent interest, but it just so happens that there are connections with the interests of many people in computer science, and I'll point some of those out as we go along. We'll begin by talking about binary trees, and then we will talk about graphs, particularly colorings of graphs. First, we'll talk about trees. You've seen trees in many contexts. You've seen factoring trees. You've seen sentence trees. Here's a sentence tree that of the type you may have seen when you were learning English. A tree is a finite directed graph, in our case, with a special node called the root. It's a source, meaning that no edges are directed into it. Every other node has exactly one edge directed into it, coming from what we will call its parent. And continuing the metaphor, it will be a child of that parent node. A node without children, mixing metaphors, is called a leaf. The definition of a binary tree will vary from book to book, but it's always going to be the case that a tree will be binary if the nodes can have at most two children. Some mathematicians, however, will state that a node must have two children or no children. We're going to look at both definitions, in fact. A picture is worth 1,000 symbols. These are all binary trees with the root at the top, which is sort of upside down. This brings us to quiz 0. In the March Madness contest, 64 teams start off playing. How many games will be played? Write your answer in binary, ones and zeros. And the answer is, if there are 2 teams, there's 1 game. If there are 4 teams, there are 3 games. These 2 teams play, these 2 teams play, and then the championship game. If there are 8 teams, there are 7 games. 1, 2, 3, 4, 5, 6, and 7. So you can see the pattern. There should be 63 games. And since 64 is 2 to the 6, in binary we should get 6 ones. 1 plus 2 plus 4 plus 8 plus 16 plus 32. Now let's count vertices and edges for trees. Throughout this unit, if we're not going to say what V is, it's generally going to be the set of vertices of the graph under consideration. and E will be the set of edges. If you look at this one-node graph, it has one vertex and no edges. This three-vertex graph has two edges. The seven-vertex graph has 1, 2, 3, 4, 5, 6 edges. And how many nodes does this graph have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This 15-node graph has how many edges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 edges. Now, we could imagine perhaps pruning this tree and removing some of the nodes and their corresponding edges. We still have a tree. How many vertices does it have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And how many edges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What's the pattern? Well, what if we don't consider a binary tree? This tree has how many nodes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And how many edges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this brings us to quiz 1. In a tree, the number of vertices will equal the number of edges, and then you should write an answer, something that will make this a correct expression. And the answer is, the number of vertices is the number of edges plus 1. We'll prove this as usual by induction. Every tree has at least one node, the root, and as we already saw, the node has no edges coming from it because there are no other nodes. Just use your calculator to check that. For our induction hypothesis, we'll assume that we've proven the theorem for all trees that have strictly fewer nodes than what we now have. So we assume that for every tree with strictly fewer vertices than the one we now have, the number of its vertices equals the number of its edges plus 1. Our tree has a leaf. Just keep going down as far as you can in the tree. Prune it. Since each leaf has exactly one edge going to it, when we prune it, we've removed one node and one edge. We have a tree with fewer vertices, so by induction, the number of its vertices equals the number of its edges plus 1. Therefore, the number of vertices in our original tree equals the number of its edges plus 1. QED.